So let's say that you wanted to find out whether there's a difference in income between males and females in Pennsylvania. We have a data set here that happens to be Pennsylvania 2016. Nice representative sample of at least the adult population. And so we go to run a t-test. This would be independent samples because we have male and female, and they're not, each person in the data set isn't meaningfully paired with another member of the data set. So it's not a paired t-test, it's an unpaired t-test or independent samples t-test. And we're going to look at income here. So as soon as you put in those two things, automatically you get a result. It's a statistically significant result. The null hypothesis would be that there's no difference between the male and female income. Our alternative hypothesis is that there is a difference. This low p-value is evidence against the null hypothesis, telling us it's likely that men and women are making different amounts of income in Pennsylvania. And maybe we don't want to just see statistical significance, we want to see some effect size here, so we grab a Cohen's d. So this is telling us on our income variable, the men are on average making 0.2 standard deviations on this scale more than females, which would be in effect maybe a low practical effect, real rough way of looking at it. We might also realize that this is just for the sample, so the 6,000 people in our study. If we're going to look at the entire state of Pennsylvania, probably that effect size is somewhere between 0.168, 0.270. Now all of this seems fine and well. Maybe we glance down here and see Levine's test is significant. What's this? We haven't talked about Levine's test. This is just one of the assumptions in order to run a t-test. You assume that the variance in the one group is the same as the variance in the other group. And if that's not the case, then technically you shouldn't run this, what's called this student t-test or this unpaired t-test, independent sample t-test. It needs a little correction factor. Luckily, that's very easy. That's called the Welch. So this is still a parametric test like we've been used to. And it corrects for this unequal variance issue. Instead of just throwing them all together as a single variance, it adjusts for it. And as you'll notice here, it really didn't make much of a difference at all. And some people say that you should always use Welch, just because if it does make a difference, then you probably want to use Welch anyway, because that's the more correct one. If it doesn't make a difference, then it really doesn't matter which one you use, so you might as well use Welch. So that takes care of that little issue. If you notice, we don't get an error here, and it seems like all is good and well. Another issue, though, with an independent samples t-test is that there's an assumption that both that the variables that you're looking at are normally distributed. And if we grab a distribution here, let me see if I can find it. Okay, here's the distribution of that income variable. It's clearly not normal. It's really not even close to. It's what we call exponential distribution. It's just getting bigger and bigger and bigger. So clearly not a normal distribution. However, because our sample size is so high here, and if I would run some descriptives, you'd see that this is also telling me that it's up around 6,000 participants here. Our sample size is plenty big enough. You'd want about 30 in each group, in the male group and in the female group, to feel confident about using a different type of distribution in this test. So the fact that our distribution isn't normal, that doesn't bother me. too much. What does bother me though is if we look at that income variable, and we look at how it was ranked, basically if the person was making less than 10,000, they were a 1, less than 15,000, they were a 2, and so on. So here it's 5,000 per category. If you jump down here to the higher ones, here it would be 15,000. In this category, here it's 25,000. Here it's, I mean, people who make millions are going to be in the same category as people who make 75,000. So it's clearly not an interval variable. It's certainly not a ratio variable. Ratio would say someone who's in category 8 is making twice as much as someone who's in category 4, and that's clearly not the case. But it's not even an interval where each interval is an equal jump, and it's not even close to that, especially with this big one right here. That one does concern me a little bit more because this is an ordinal variable. I mean, they are in rank. Someone who scores a 7 is making more than someone who scores a 3, but we don't really have a good way of comparing them in between. And so when we start talking about averages, this gets a little bit dangerous. So what do you do if you're a researcher in this situation? You have a clear, well-defined question. You don't happen to have any better income data than this ordinal data. And you want to be able to tell if the male and female are making different amounts. Well, here's where a non-parametric test can come in to save the day. And the Mann-Whitney is the non-parametric version of the unpaired t-test, or the independent samples t-test. So all we have to do is click that, and we're going to see the results down here. And so what do we notice? First of all, it's also statistically significant. The non-parametric tests tend to have less power than the parametric test. And what that means is if there really is a significant difference, in this case, if men and women are really making different incomes, it's not going to be able to pick up on that difference as easily as one of these parametric tests are. So the p-value will tend to be higher in your non-parametric test than in your parametric test. In other words, it's harder to reject the null with the non-parametric. So you're paying a price for the fact that the good part is you don't need to assume that the data is normal. You don't need to assume that it's even an interval or ratio variable. It's okay that it's an ordinal variable, but the price you pay for that is it's going to be a little harder to reject the null. In this case, the difference between the two groups and their incomes is strong enough that we still have statistical significance even with this non-parametric. If, by the way, you're not sure whether to use the non-parametric or parametric, you use a non-parametric and you get a statistically significant result, you can rest assured that the result is statistically significant. Because it's a more conservative test, if you're able to reject the null with a non-parametric, then it probably would be much easier to reject the null with the parametric version. So you can it's kind of a conservative way to run the test. So here we see that we do have a smaller effect size, and this is probably a little more accurate. We're essentially assuming that the male and female distribution is the same. We could look at that, but essentially we're looking at is the median male income different than the median female income. We're seeing that yes, it probably is. Again, we have, just like with the parametric, we have a confidence interval for what that effect size really is. And the way it looks, it's pretty certainly there. I mean, even in the worst case, there is some difference between the incomes. Not a real strong effect size here. And this is where we would need to go in. My hunch is, like, you might think to yourself, and this is what I'm thinking, that males make quite a bit more than females. We should see more practical significance here. And I think that's absolutely correct. The the reason we're not getting that is because of the way the data is coded, because this is all lumped together in a single category. And so you're going to have more male multimillionaires, for example. And those multimillionaires, the power of their salary is not going to show up on this scale because it cuts off at 75,000. So it's still not a perfect, it's not a perfect way to look at the data. Ideally, you'd have actual incomes instead of just these income brackets. But given what we have, we can still make the conclusion using a conservative estimate here based on this ordinal variable that men are making more than women in Pennsylvania. Now, I should also add that this doesn't at all take into account men and women of the same position. I mean, there could be a lot more men in higher ranking administration positions. And this would not be, if we wanted to do that, we'd somehow have to control for that, the ranking of each person too. There are ways, there are data sets that do that. I'm not sure that this data set does that. But there have been studies where they go in and look a little more closely at that gender pay gap to investigate, is it really there? What's it related to? And how strong is that gap?